Hi everyone. So this is a third video in a series about looking at topographic information and manipulating rasters in Google Colab and using some geospatial tools, mainly something called gdal, which is short for the Geospatial Data Abstraction Library. We're going to do lesson 3 today, or in this video. So if you go into my GitHub page where I've got some teaching notebooks, you can click on this one, lesson 3, and click on open in Colab, and you end up here in a Colab session. And I've already done these first 3 steps because they take about 1.5 minutes. So that's installing a couple of tools that we use in all of these notebooks. One of the things that happens in Google Colab is that you need to install the Geospatial Data Abstraction Library. It looks for this database of projections and transformations, and as of September 2023, it can't find it. So you need to tell it where it is. So there's this 4th cell here, which basically tells the system where the library is. So I'll just execute that, and now everything should work. Okay, the next bit is that we're going to use a little wrapper that I've written that allows you to download data from a brilliant website called opentopography.org. So you use a package called LSD Viz Tools for that. So I've already, if you're in Colab, we've installed this first. It's already up to date. You don't need to do this step here, but we can import all the things we need. And then what we're going to do is grab data from OpenTopography. And again, I'm using this wrapper function that I've written in LSD Viz Tools. To use that wrapper, you need to have an API key as inside of a text file. So the API key is a bunch of letters and numbers. You get that from opentopography.org once you sign up to them. Do not share your API key. So I've got that as a file. I click on the file area of Google Colab, and I just drag that in. So I'm just going to drag my key in here. And again, in Google Colab, files are not persistent. That's why I got that little warning. So once I close this session, these files will disappear. Okay, so I use this little bit to download some data, and the way the data download wrapper works is you give it the latitude and longitude of the lower left and upper right corner of the area that you want. So I'm just gonna, I've assigned the lower left and upper right corner of it, and then I use this little bit to download the DEM. I'm going to download several versions of the DEM here. So this is the SRTM 90 meter data. The 3 is for 3 arc seconds, which equals around 90 meters. It's not quite 90 meters because this site is not at the equator. This is the 30 meter SRTM data set. And this is the 30 meter Copernicus data set. So SRTM was collected by radar data flown on the shuttle, the space shuttle, and that was collected in 2000. Copernicus 30 is much later data, so collected in the late-ish 2010s. So I just download all 3 of these, and I'm going to get 3 different DEMs. And I just wait for that to download. So what I want to do is take these data sets, and I'm going to project them using gdal warp. So I talked about gdal warp in the previous section. The syntax, again, you have gdal warp, and you're calling it from command line, so you have this exclamation point in front. You're telling it what the target coordinate reference system is with this bit of the code, and we're using a UTM zone. So the UTM zone is zone 30, and the EPSG code for that is 32630, zone 30. You can find maps on the internet of what UTM zone you have. So there's big maps. It's easy to look up your site what the UTM zone is. If you get the UTM zone off by one zone, you'll only have a fairly small amount of distortion. So don't worry too much about getting one zone off. If you're 2 zones off, you start getting more distortion. 3 zones off, you're probably in trouble. So try to get the right zone, but if you're off by one zone, it's okay. The next bit of this, so I'm telling it the input file, and then I also give it the output file. I resample it using the cubic method, and in the previous video I explained why it's really essential to use this cubic method. You can also use bilinear, but do not use the default. The default will give you artifacts on your DEM, and then I set the target resolution of the DEM, 30 meters by 30 meters. And this one, 30 meters by 30 meters, and then the other one, the last one, is the 90 meter DEM, so I'm doing it 90 meters. Okay, then I'm going to make a hillshade from all of these output rasters. So I tell it to make a hillshade, I tell it what the input raster is, I tell it what the name of the output raster is. I always use HS after the raster to designate the hillshade, and I use this algorithm, which looks nicer than the default algorithm. So let's just go through all 3 of these. Okay, then what I'm going to do is I'm going to look at the data using rasterio. That's a package for looking at geospatial data in Python. So I'm just loading all these hillshades into rasterio objects. That's what that does. And now I can plot them. So it's a little bit small in this screen, but what you should see, so this is the SRTM 30 meters. If you compare that to the 90 meter, you can see how it's just lower resolution, it's blurrier. So this has more detail. I think if you look around this area in the center of the DEM, you have that. And then you have this much more sharper, so it's a higher resolution. What about the Copernicus 30? So I'm not going to scroll back and forth. I'm going to put these side by side, and I'm going to zoom in just because it's easy to see. So what I'm doing here is I'm zooming in on a certain part of the plot, and I'm going to look at the 2 DEMs. So these are both 30 meter DEMs, but as you can see here, the Copernicus DEM is much sharper. So there's a bit of post-processing that went into making it look like that. But in addition, Copernicus is based on mostly radar data from this Tandem X satellites, and those produced a 12.5 meter resolution DEM. That was the original DEM. So Copernicus has been made mostly from that DEM, and also a lot of data checking, data quality went into that. So that's why it looks a bit less noisy than the SRTM 30 meters. Right now, in terms of the global 30 meter DEMs, Copernicus is probably the best one. The ALOS 3D, World 3D 30 meter DEM is also quite good. So I also wanted to show you what some of the derivative data might look like. I'm just going to get the gradient from these 2 30 meter DEMs. So again, gdaldem includes a slope function. So I just run that for both of the 30 meter DEMs. And then again, what I'm going to do here is I'm going to use rasterio to get a histogram of the gradient. Actually, I just lied. I'm using SRTM compared to SRTM3. So it's the 30 meter SRTM and the 90 meter SRTM. Okay, so let's look at the histogram of gradients in 30 and 90 meters. So what do we see here? We see that you basically get steeper slopes. So you can see the kind of histogram. You push out the density of the higher slopes in the 30 meter data. So the slope is gentler in the 90 meter data. This is systematic. Coarser topographic data underestimates topographic gradients. And you also get biases if you take other derivative data. So for example, curvature is another topographic derivative that we use quite a lot. The lower resolution your topographic data, the more biased your output will be. So this is just a little illustration about how you should be careful about choosing the data size. If you're looking particular at gradients on hill slopes, if you're doing landslide things, you really ought to use as high resolution as you can, but 30 meters is a lot better than 90 meters. If you can get 1 meter LiDAR, that's kind of the gold standard. So hopefully this has been useful. You can see how to warp and project different DEMs, download DEMs of different resolutions, and look at a few statistics about them just using gdal and rasterio.